Okay, so number one, find the derivative for this equation. Oh, we always want to consider log expansion before we do anything with derivatives. So yeah, you guys can get out a sheet of paper. I'm just going to create some problems for us to work on. Okay, so just to kind of remind us, log expansion can also be applied for logs of other bases. So as a reminder, if I have multiple terms inside my log or natural log expression, anything in the numerator is going to be part of a positive log term. Anything in the denominator is going to be part of a negative log term. Okay, so a couple of reminders about derivative rules. Okay, but first things first, we see a total of 3 terms. So we're going to split them up. And as we split them up, keep in mind that the 4 is going to tag along to every term. Hi. Oh, that's right. Yeah. Okay. Next in the back. Okay, so start with expansion. And the reason why we want to expand is because otherwise if we jump directly into our derivative rule, this is such a messy u value. We would prefer not to find the derivative of something that's in this form, right? Then we got to go through quotient, product, and chain. It's not ideal, right? Okay, so we really want to take advantage of logs. And also, the second thing is we don't do log differentiation with this, right? We save log differentiation for problems that have no logs in it. If there's already logs in it, it's ready for expansion. If we reintroduce logs, we're going to make the problem more complicated, right? So this is ready for log expansion. So I'm cleaning up as I go along. Okay. Once we're part of a log term, we can bring the exponents down in front. No exponents here. We can bring the 1/4 down in front. All right, so now we've expanded as much as we can. We're ready for our derivative rule, right, for log base 5. Basically, u prime over u with a little bit of conversion into base e that needs to happen. We have 20. Now, log base 5 of e, this is really just a number, right? So imagine writing it this way, that this is really 20 log base 5 of e times x. So this is really a linear term. If I have let's say 6x, what does 6x turn into? Just 6, right? So 20 log base 5e is just a messy number in front of a variable. That's just going to turn into just 20 log base 5 of e, right? E is just a number. Normally by itself, this would be 0, but that x is just going to force us to keep that coefficient. Okay, moving on. Keep the 4. Log base 5, we get that 1 over natural log of 5. And then u prime over u, what does 3x become? 3 over 3x. Which we can cancel out. The 4's go away. We have 1 over natural log of 5. And then u prime over u. I think that's basically it. We can do kind of rearrange things a bit, but we basically have our derivative. Okay, any questions with 1? Okay, so here's number 2. Okay, so first things first, let's just go ahead and rewrite this problem, right? We want to represent this using rational exponent and not radicals. So what will this look like? Raised to what? 5 over x. Okay, so how do we approach this problem? What does this look like to you? So I heard chain, but not quite. It would be good chain rule if it was just that 5 there. But that x kind of throws a wrench into that process. So we actually don't have a rule for this. This is a variable expression raised to a variable expression. So we have to force it into a different form. How do we force this into a different form? You guys remember? Is there something that we can do to make this exponent be somewhere else? Okay, so this is where we have to involve log differentiation. So log differentiation is where we introduce logs into the problem so that we can take advantage of log properties because of this dead end that we're kind of experiencing here. Okay, so, but first we need to recognize that this is something that we don't have a rule for, right? This is not power rule. This is not chain rule, even though it kind of looks like it, but I mean, if that x wasn't there, it'd be fine. But that x being there kind of causes an issue. Okay, so log differentiation to allow for expansion, and then we can move into a proper derivative rule, okay? So we'll take the natural log of both sides. Now, I want to rewrite this as 5x to the negative 1, just because when it comes down, it'd just be a lot cleaner to find a derivative relying on power rule than having to go through like a quotient rule just for that little 5 over x, right? Okay, now what can we do? What can we do with this exponent now? Yeah, push it down, right? This is now log property. There's no derivatives going on here. We're just expanding, just bringing that exponent down. Okay, now we have rules more available to us. Okay, left side is u prime over u. This is implicit. And the right side, look at how this is set up. We have to involve what besides the rules we see in front of us? Product rule. Okay, so this is f, this is g. We got to go through the product rule there. Okay, 1 over y dy dx. F prime, power rule. Bring down the exponent, subtract 1 from the exponent. G function, copy everything down. Back to F. And now G prime, okay, we can't expand this any further, okay? We can't distribute the natural log through. Okay, but we can't do U prime over U. It's a little messier here. Our U value is this whole mess here. So we need to find that whole derivative of this and put it over the original U value, okay? So the rule for e to the 3x is e to the 3x times 3. And then here, there's a little mini U prime over U going on here. So this is 2x over x squared. All over my big U value. Okay, so we can leave this whole derivative as one big mess. So we just have to bring the y over to the right side, kind of isolate dy dx, and then we can resolve that last substitution, replace y back in terms of the original expression. And then bring the original problem back. Okay, any questions? Are there any parts you want me to kind of re-explain or go over in more detail? Okay, everybody good here? All right, here's number 3. Okay, we want to find the derivative of the inverse at a point. However, we're not given the inverse function, we're given the original function. So the first thing we have to understand is that even though you're looking at the x value of the inverse, really, in terms of the function, this is the what? Not the x, but the y. Okay, so that's got to be the first thing we understand. If we start inserting this 4 into the x, it's going to throw everything off. Okay, so that's really the big hurdle here. Understanding that there's that flipped relationship in terms of the x and y. So understand this is really the y value. Okay. So we have to spend the time to basically figure out what the x value is and build that order pair. And then once you get the x value, we can find the derivative, find the slope, and then we can turn back around and figure out what the slope of the inverse. Okay. So I like to use this chart. You don't have to use this chart, but just helps keeps my information organized. My ultimate goal is to figure out the slope of the inverse at 4, but I'm not going to do anything on the inverse side of things. I'm doing everything on the function side of things. So I know my order pair is going to stand as 4 something on the inverse, but it's really that 4 is the y value of the original function. So my order pair here. Okay, so this is where my work is going to come in. I'm going to figure out what the x value is when the y is 4. Once I figure that out, then I can find the slope at a point. And once I find that slope, then that slope is going to lead me to the slope of the inverse, because these slopes will always be reciprocals of each other. Okay, so we'll set 4 equal to the function. These problems are not going to be factorable. We're going to have to just go through a series of guess and check. So bring everything over to one side, and we'll go ahead and test out some numbers to see what's going to make this a true statement. These numbers should be easy to find. You want to just find numbers around 0. Let's see, does 0 work? No. How about 1? 1 cubed is 1, 1 minus 3 is -2, -2 minus 2 is close, right? Not quite though. How about x equals -1? -1. Let's see. Yeah, -1 works, right? Sorry, I didn't mean for there to be 2 different solutions. I think 1 also works. Okay, but we'll go with -1. Okay. -1. Oh, let me see. -1 plus 3 minus 2. That works, doesn't it? Okay. You don't think what? Yeah, 1 doesn't work. I think 2 also works. Yeah, 2 also works, but we'll go with -1. Okay. But we understand that this is how we find the appropriate x value. So now that we have things set in place, now we can go to our derivative. Right? Find the derivative, evaluate the derivative, and then find the slope. Okay. F prime of x. What's f prime? Now we have the proper information to evaluate the slope. Sorry, it's not a great example here. This ends up being 0. And then if we flip it, it'll be undefined. Okay, but what you're going to see on the test is more whatever number you get, you're just going to flip that, get the reciprocal, right? So if it was 3, then you'll make it 1/3. If it was 5, you'll make it 1/5. But this is kind of like a strange example. If this is 0, if I flip 0, it's going to be undefined. But I didn't test out this problem before I created it. But do you guys see the big idea, though? Okay. So whatever slope you get here, technically, you'll get to flip it. And once you flip it, that's the slope that you're really after. So if you get 8, you make it 1/8. If it's 2/3, you make it 3/2. Don't change the sign, just flip the ratio. Okay. All right, let's do an implicit problem here, number 4. Let me change this. Minus x y squared. Okay, can you list out what's necessary in order to work through this problem? What do you see? Okay, so definitely implicit, right? You got y's all over the place. What else? Product rule, right? There's x, y squared there. What else? Quotient rule, but is there a way that we can avoid quotient rule? What can we do here? Yeah, log expansion, right? So quotient property, how about that? Log expansion. So that's actually what we want to do first. We want to get that out of the way before we have to go through our derivative. Otherwise, if we do u prime over u, this is a pretty messy u value that we prefer to avoid. Okay. So let's take care of that first. Natural log of A over B is same thing as natural log of A minus natural log of B. Okay, so now we're ready for our derivative rules. U prime over U prime over U. We got to go through product rule here. I put this in parentheses so as a reminder that once I'm done with product rule, I still got to remember that the negative is going to have to distribute through the parentheses. Power rule, and then implicit along the way. Okay, if I count 3 y's, I should be expecting 3 dy dx's to pop up. Okay, one term at a time, 1 over x. We can't bring the 2 down. Do you know why? Thank you. Does anybody know why? Why can we not bring this 2 down in front? Okay, that's true, but that's not the reason. Why can this 2 not just come down in front before we do our power rule? Okay, it's not a log term. You can bring it down if it's part of a log term, but otherwise, if it's not part of a log term, if you bring it down, you're changing the problem. It's not the same thing anymore, right? Or we can't just bring an exponent down unless it's part of a natural log or log expression. Okay, so this has to stay. Okay, f prime g plus f g prime. X becomes 1. G is y squared. Back to f. And then g prime, y squared becomes 2y dy dx. Five x becomes 5. And then 6y becomes 6 dy dx. Okay, we're done with our derivative step. The rest is just trying to clean all this mess up, trying to group all the dy dx together, factor it out, and then solve for dy dx. Okay, but any questions up to this point? All right, the hardest part is just trying to get to the derivative, get through this derivative step here. But from here, it should be a lot easier. No questions? Okay. Okay, I'm just going to add and subtract terms, group the dy dx terms all onto the same side. Okay, if you group them on a different side, our negative signs may look a little different at the end, but that's fine. Okay, any questions here? Okay, yeah, we hit a lot of these smaller problems that you're going to see on the test, right? Derivative inverse at a point. We did log differentiation. We did implicit differentiation. We did expanding log terms. We did logs of exponentials of base E and base A. Well, we didn't do exponentials of base A, but you know, that's just the natural log of A times A to the U times U prime. We did a little bit of product rule, and we didn't do tangent line equation, but we did that yesterday. That's just find order pair and slope in point slope form. So today in class, we'll continue working through our two major topics, okay, two larger problems. And then tomorrow morning, I'll have a morning review session, and it's morning review worksheet 4. That's on the website. You guys can get a head start on that if you like, but you can join on the help session tomorrow, 7:15 as well. Okay. All right. See you guys in class.